Look up at the stars tonight and let yourself really take it in, the vastness, the silence, the countless points of light stretching endlessly into the darkness. It's a view that's remained unchanged for millennia, yet it holds mysteries so profound they defy everything we think we know about the universe. Even with our most powerful telescopes, supercomputers, and brightest minds, there are cosmic puzzles that leave scientists utterly stumped. Some of these enigmas shake the very foundations of physics, while others hint at realities beyond our wildest imagination. What if I told you that right now, as you're watching this, there are forces at work in the cosmos that shouldn't exist, phenomena with no explanation, no logical framework, just gaping question marks hanging in the void? This is the frontier where science meets the unknown, where the rules we've relied on for centuries seem to bend or break entirely. Take dark matter, for example, an invisible substance that makes up most of the universe's mass, yet we've never directly seen it. Or consider fast radio bursts, explosive signals from deep space that last mere milliseconds, pulsing with more energy than our sun emits in days. And then there's the eerie Great Attractor, a gravitational anomaly so powerful it's pulling entire galaxies toward it, yet we can't even see what's causing it. These aren't just curiosities, they're glaring gaps in our understanding, reminders that the cosmos operates on a scale we're only beginning to grasp. So why do these mysteries matter? Because every unanswered question is a doorway, a chance to rethink what's possible. They force us to confront the humbling truth that for all our progress, we've barely scratched the surface of the universe's secrets. And that's exactly what makes this journey so thrilling. Over the next 36 interstellar enigmas, we'll explore celestial oddities that challenge logic, phenomena that rewrite the rules, and discoveries that blur the line between science and science fiction. By the time we're done, you won't just see the night sky differently, you'll feel it. The universe isn't just a static backdrop, it's alive with mysteries waiting to be unraveled. Ready to dive in? Let's begin. Picture this. It's a quiet night in Ohio, 1977. A massive radio telescope known as the Big Ear is silently scanning the cosmos, listening for whispers in the static of space. Then suddenly it happens. A burst of radio waves, narrow in frequency and blazingly intense, erupts from the constellation Sagittarius. For 72 seconds, the signal floods the receiver, so strong and unnatural that astronomer Jerry Amon circles the data on the printout and scrawls a single word in the margin: "Wow." And just like that, it vanishes. No trace, no repetition, no explanation. Decades of searching later, we're still left with that same electrifying question. Was this humanity's first brush with an alien hello? What makes the wow signal so haunting isn't just its strangeness, but the way it defies every attempt to explain it away. The signal matched the exact frequency that hydrogen, the most common element in the universe, emits naturally, a logical choice for an advanced civilization trying to get noticed. But natural cosmic phenomena don't behave like this. Pulsars repeat, quasars flicker. This was a one-time scream in the dark, surgically precise and eerily deliberate. Even today, theories swing between two extremes. Was it a bizarre celestial fluke, like a comet's hydrogen cloud reflecting sunlight in just the right way? Or something far more profound, a beacon from a distant intelligence, turned on just long enough to make us wonder? The chilling truth is, we may never know. But that's the power of this mystery. It lingers in the back of every astronomer's mind, a reminder that the universe might not be as empty as it seems. Imagine what it would mean if that signal was intentional. Somewhere out there, another civilization aimed a transmitter our way, knowing the message would take centuries to arrive. Or worse, what if we missed the reply? The wow signal isn't just a scientific curiosity. It's a cosmic riddle that taps into our deepest hopes and fears about what or who else might be waiting in the dark. And until we hear it again, that single word on a faded printout remains one of history's most tantalizing maybes. Now, let's shift our gaze to something even more perplexing: dark matter. Imagine holding up your hand and seeing right through it, not because it's transparent, but because it's made of something entirely invisible, something that doesn't reflect, absorb, or emit a single shred of light. That's the eerie reality of dark matter. It's everywhere, woven through the cosmos, exerting an unmistakable gravitational pull on galaxies, yet it slips through our detectors like a ghost. We know it's there because without it, galaxies would fly apart, their stars scattering into the void like marbles dropped on the floor. But what is it? That's where the mystery deepens. Think of the universe as a grand cosmic ballet. The stars, planets, and galaxies we see are just the dancers in the spotlight. But the stage itself, the scaffolding holding everything together, is dark matter. It doesn't dance, it doesn't glow, it just is, silent and unseen. Scientists have spent decades chasing shadows, proposing exotic particles like WIMP, weakly interacting massive particles, that could explain its presence. These hypothetical particles are like cosmic ninjas, barely touching ordinary matter as they pass through it. Yet, despite colossal experiments deep underground, in abandoned mines and beneath mountains, where detectors wait like traps for a single, fleeting interaction, dark matter remains stubbornly elusive. Here's what makes this so unsettling. Dark matter isn't some minor curiosity. It makes up roughly 27% of the universe. That's 5 times more than all the atoms, planets, and stars combined. And yet, it refuses to play by the rules we've written for everything else. Ordinary matter interacts through forces we understand: gravity, electromagnetism, the strong and weak nuclear forces. Dark matter, it seems to care only about gravity, ignoring the rest like a stranger walking past without a glance. Some theories suggest it might be part of an entirely hidden sector of physics, a parallel universe of particles and forces operating just beyond our perception. The implications are staggering. If dark matter is real and the evidence says it is, then everything we see, everything we are, is just the tip of an iceberg floating in an ocean of the unknown. It's humbling, even a little terrifying, to realize that most of the universe is made of something we can't see, touch, or even comprehend. And until we crack this puzzle, we're left with a cosmic detective story where the culprit leaves no fingerprints, no traces, just the undeniable fact that something out there is holding the stars together. The hunt continues, and with every dead end, the mystery only grows more profound. Now, let's talk about something that sounds like it's straight out of a sci-fi thriller: fast radio bursts. Imagine a signal so powerful, it unleashes more energy in a single millisecond than our sun does in 3 days. Now imagine that signal traveled halfway across the universe just to flicker across our telescopes for a fraction of an eye blink, then vanishes without a trace. That's the enigma of FRB's cosmic Morse code from galaxies so far away. Their light takes billions of years to reach us, and the strangest part, we still have no idea what's sending them. Some of these bursts are one-hit wonders, appearing once and never repeating. Others, like FRB 121214, pulse on a loop like a cosmic heartbeat with no discernible rhythm. At first, astronomers wondered if they were the death cries of neutron stars collapsing into black holes, a final, violent farewell. But then, why do some repeat? Others theorized they might be the result of magnetars, ultra-dense stellar corpses with magnetic fields so strong they could strip the electrons from your atoms from 1,000 light-years away. Yet even that doesn't explain the burst's jaw-dropping energy or their bizarre patterns. Then there's the wildcard theory. Could these be signatures of advanced alien technology? Before you dismiss it, consider this. A civilization capable of harnessing the energy of an entire star might use focused beams like interstellar lighthouses to navigate or communicate. The idea isn't as far-fetched as it sounds. In fact, some researchers have calculated that a transmitter the size of a planet, powered by a star's energy, could produce bursts exactly like the ones we're detecting. Of course, there's no proof, just the unnerving possibility that we might be eavesdropping on someone else's engineering. What makes FRBs so frustrating and so fascinating is how they defy categorization. They're like cosmic fingerprints with no matching suspect. Every time we think we've pinned them down, a new burst appends our theories. Take FRB 190520, for example. It wasn't just loud, it came with a side of visible light, something no other burst had done before. Was it a cosmic collision, a starquake on a scale we've never witnessed? Or something entirely beyond our current physics? The truth is, fast radio bursts are more than just deep space oddities. They're clues. Every time one crackles through the void, it carries encoded information about the fabric of the universe itself, the dust, the magnetic fields, even the missing matter between galaxies. Cracking their code could rewrite our understanding of the cosmos, but for now, they remain one of astronomy's most electrifying puzzles. A reminder that the universe loves to keep us guessing. And as we listen to these fleeting whispers from the dark, one thing is certain: the answers, when they come, will be stranger than anything we've dreamed up so far. There's a question that lingers in the silence between the stars, one so unsettling that even the brightest minds hesitate when they try to answer it. The universe is unimaginably vast, with hundreds of billions of galaxies, each home to hundreds of billions of stars. Statistically, the numbers scream that life should be everywhere, so where is everyone? This is the Fermi Paradox, a cosmic riddle that cuts to the heart of our loneliness in the cosmos. Named after physicist Enrico Fermi, who famously blurted out during a casual lunch discussion, "But where are they?" The paradox confronts us with a glaring contradiction. The universe is old enough, big enough, and rich enough with ingredients for life to have spawned countless civilizations. Yet our telescopes and radios hear nothing but static. One explanation is as simple as it is sobering: maybe we're alone. The conditions for life, let alone intelligent, spacefaring life, might be so vanishingly rare that Earth is a fluke. A cosmic lottery ticket pulled against impossible odds. Think of it like this: even if a planet sits in the habitable zone with water and the right chemistry, it might still need a moon like ours to stabilize its tilt, or a Jupiter-like neighbor to deflect deadly asteroids. Tweak one variable and the dominoes of life never fall. But there's a darker twist. What if life is common but intelligence is a dead end? Civilizations might rise, only to crumble under climate disasters, nuclear war, or runaway AI long before they ever reach the stars. The universe could be littered with the ruins of civilizations that burn too bright, too fast, or worse, what if advanced species choose silence? Imagine a galactic neighborhood where every civilization hides, fearing predators that hunt for signals like ours. It's a chilling thought. The reason we haven't heard anyone might be because the first rule of Space Club is don't scream into the void. Then there's the mind-bending possibility that we're just too primitive to recognize the evidence. An advanced civilization might communicate in ways we can't fathom using neutrino beams, quantum entanglement, or structures so vast, like Dyson spheres harvesting a star's energy, that we mistake them for natural phenomena. They could be all around us, their presence as invisible to us as Wi-Fi signals would be to a medieval peasant. the Fermi Paradox isn't just about aliens. It's a mirror. Every theory reflects our hopes, our fears, and our understanding of ourselves. Are we the universe's firstborn, its last survivors, or simply its quietest neighbors? Until we find proof, the question hangs in the air, heavier than the silence of the stars. And perhaps that silence is the answer, a reminder that the universe doesn't owe us company. But the search continues, because if we are alone, that makes every one of us, and this pale blue dot we call home, infinitely more precious. Deep in the constellation Cygnus, about 1,500 light-years from Earth, a star behaves like nothing else we've ever seen. Officially catalogued as KIC 8462852, but better known as Tabby's star, named after astronomer Tabetha Boyajian, who first brought its strangeness to light. This unassuming flicker in the night has become one of modern astronomy's most tantalizing puzzles. At first glance, it seems ordinary, but then you notice the dips. Not the gentle, rhythmic dimming of a planet passing in front of it, but wild, irregular plunges in brightness, sometimes by as much as 22%, as if something enormous and unpredictable is drifting between the star and us. Theories scramble to explain it. One of the most provocative, alien megastructures. Imagine a civilization so advanced, it's built a Dyson swarm, a colossal network of energy-harvesting panels encircling the star, capturing its light to power a society beyond our imagination. The idea isn't entirely science fiction. Physicist Freeman Dyson once speculated that such structures would be the inevitable mark of a civilization reaching for the stars. And Tabby's star's erratic dimming fits the profile, uneven, massive, and utterly unlike anything natural we've observed. But before we jump to extraterrestrial conclusions, nature offers its own bizarre possibilities. Maybe it's a swarm of comets, thousands of them, fractured and dusty, trailing in a chaotic orbit that occasionally blots out the star's light. Or perhaps it's interstellar debris, a vast cloud of dust and rock left over from some ancient cosmic collision, drifting across our line of sight. There's even a chance the star itself is to blame, with some unknown, hyperactive stellar phenomenon causing it to flicker like a dying light bulb. Here's the catch: none of these explanations quite fit. Comets would leave telltale infrared signatures from their heat, which we don't see. Dust would scatter light in predictable ways, but Tabby's star dims unevenly across all wavelengths. And as for natural stellar behavior, we've catalogued millions of stars, and not one behaves like this. Every time we think we've pinned it down, the star throws another curveball, like in 2017, when it dimmed suddenly again, sending astronomers scrambling for their telescopes. What makes Tabby's star so compelling isn't just the mystery of what's blocking its light, but what that answer could mean for us. If it's natural, we're staring at a new astrophysical phenomenon that could rewrite textbooks. If it's artificial, well, that changes everything. Either way, this tiny pinprick of light reminds us that the universe is still full of surprises, and sometimes the most ordinary-looking things hide the most extraordinary secrets. Somewhere in the vast cosmic darkness, beyond the familiar stars and galaxies we map in our textbooks, there's a force so immense it's tugging at the Milky Way like an invisible leash. Astronomers call it the Great Attractor, and it's not just pulling us, it's dragging hundreds of thousands of galaxies toward it at speeds exceeding 1 million miles per hour. The strangest part, we can't even see what's doing the pulling. This colossal mystery lurks behind what scientists call the zone of avoidance, a region of space obscured by the thick dust and stars of our own galaxy's central bulge. It's like trying to peer through a fogged-up window while hurtling toward whatever's on the other side. At first, researchers thought this gravitational monster might be a supercluster, a dense knot of galaxies with enough combined mass to bend the fabric of space-time itself. But when they mapped the visible matter in that direction, the numbers didn't add up. The pull was too strong, too concentrated. Then came the real shocker. The Great Attractor isn't the end of the journey. It's just a waypoint. Beyond it lies something even more massive, an unfathomable structure dubbed the Shapley Attractor, a gravitational behemoth 8 times the size of our local supercluster. Together, these cosmic anchors are yanking entire galaxies across the universe like beads on a string. So what's really out there? One theory suggests dark energy, the same mysterious force accelerating the universe's expansion, might be warping space in unexpected ways, creating phantom gravitational pulls where none should exist. Others speculate about primordial flaws in the universe's structure, leftover wrinkles from the Big Bang that collapsed into knots of invisible mass. And then there's the spine-tingling possibility that we're seeing the fingerprints of higher dimensions, where gravity leaks into our reality from realms we can't perceive. The irony is crushing. We're being dragged toward something we can't see, by forces we don't understand, toward a destination that might not even be the final stop. It's a cosmic reminder that for all our telescopes and equations, the universe still holds cards it hasn't shown us. And as we race toward the Great Attractor at 1,000 kilometers every second, one question lingers. When we finally see what's pulling us, will we wish we hadn't? In the vast emptiness between planets, where the sun's grip weakens and the laws of physics should be predictable, something strange happened to 2 of humanity's most intrepid explorers, the Pioneer spacecraft. Launched in the early 1970s, Pioneer 10 and 11 were designed to push beyond the asteroid belt, to Jupiter, Saturn, and eventually into the abyss of interstellar space. But as they drifted farther from Earth, scientists noticed a tiny, persistent tug slowing them down, a deceleration so slight it was barely measurable, yet utterly inexplicable. Every known force had been accounted for: gravity, solar radiation, even the faint push of cosmic dust. But the numbers refused to add up. Pioneer 10, for example, was falling behind its predicted trajectory by about 300,000 miles every year, as if an unseen hand was gently pressing the brakes. At first, researchers wondered if they'd stumbled upon a flaw in Einstein's theory of gravity. Could there be some hidden quirk in the fabric of space-time that only revealed itself in the quiet outskirts of the solar system? Others speculated about dark matter. Perhaps the spacecraft were plowing through an invisible halo of the stuff, its gravitational drag throwing off their speed. The idea was tantalizing. After all, if dark matter could shape galaxies, why couldn't it nudge a lonely probe? But there was a problem. No other spacecraft, not even Voyager hurtling through similar depths, showed the same anomaly. Then came the thermal theory. Pioneer's nuclear power source constantly emitted heat, and that heat radiated unevenly from the spacecraft's body. Over decades, even the tiniest imbalance could create a recoil effect, like a garden hose thrashing backward as water spurts out. Computer models eventually showed this could explain most of the drift. Case closed, not quite. While thermal radiation likely played a role, some discrepancies lingered, leaving room for doubt. The anomaly became a lesson in humility, a reminder that even in the cold, calculated world of orbital mechanics, the universe can still spring surprises. What makes the Pioneer anomaly so compelling isn't just the mystery itself, but what it represents. For years, it forced scientists to question whether they'd missed something fundamental about the cosmos. It's a reminder that exploration doesn't just reveal answers, it exposes gaps in our understanding, gaps we didn't even know existed. And while most researchers now accept the thermal explanation, a whisper of uncertainty remains. Because sometimes the smallest deviations lead to the biggest revelations. After all, it was a tiny wobble in Mercury's orbit that helped prove Einstein right. Who's to say Pioneer's hiccup won't one day do the same? It streaked through our solar system like a silent bullet, moving too fast to be from around here our first confirmed visitor from another star. In October 2017, the Planck Stars telescope in Hawaii spotted it, a faint, speeding dot they named Oumuamua, Hawaiian for scout. At first, astronomers assumed it was just another comet or asteroid, albeit one from very, very far away. But as they tracked its path, that assumption unraveled. This was no ordinary space rock. Its shape alone was bizarre, a needle-like object roughly 10 times longer than it was wide, tumbling end over end like a cosmic cigarette. Nothing in our solar system looks like that. Then came the real shocker. It sped up. Comets accelerate when sunlight vaporizes their ice, creating a glowing tail of gas and dust. But Oumuamua had no tail, no visible outgassing at all. Yet something was giving it an extra push, nudging it off the trajectory gravity alone dictated. The explanation, that's where the debate erupts. One camp argues it's a hydrogen iceberg, a chunk of frozen hydrogen so light that as it warmed, the escaping gas acted like invisible rocket fuel. The problem, we've never seen such an object, and hydrogen ice shouldn't survive the trip between stars. Others suggest it's a cosmic dust bunny, a fragile aggregate of particles so porous it's more like a sponge than a rock. But again, no known process creates objects like this naturally. Then there's the theory that made headlines: Oumuamua could be artificial. Harvard astrophysicist Avi Loeb famously suggested it might be a light sail, a thin, discarded relic of alien technology, coasting on starlight pressure the way a boat catches wind. The idea isn't entirely wild. Humanity has already launched prototype light sails, and an advanced civilization might litter the galaxy with them. But with no radio signals or other signs of intelligence, most scientists remain skeptical. Still, the very fact that such a theory gained traction shows how deeply Oumuamua puzzled us. What lingers beyond the speculation is the chilling realization of how little we know. Oumuamua came, intrigued us, and vanished into the void before we could study it properly. By the time we noticed, it was already racing away, a fleeting glimpse of the universe's secrets slipping through our fingers. Was it a weirdly shaped rock, a ghostly iceberg, or something even more extraordinary? We may never know, but its visit was a wake-up call, proof that interstellar interlopers are out there, and the next one might hold answers we're not even smart enough to question yet. Imagine throwing a book into a fire. The pages burn, the ink vanishes, but in theory, if you could track every ash, every wisp of smoke, you could reverse engineer the book's contents. That's the fundamental promise of quantum mechanics. Information is never truly lost, just transformed. Now, replace that fire with a black hole. The moment matter crosses its event horizon, it's gone. Not just hidden, but seemingly erased from existence. This is the black hole information paradox, a cosmic tug of war between two pillars of physics: quantum theory, which insists information is indestructible, and general relativity, which says black holes swallow it without a trace. The paradox sharpened in the 1970s when Stephen Hawking made a startling discovery. Black holes aren't entirely black, they leak. Through a bizarre quantum effect near the event horizon, they emit faint radiation, now called Hawking radiation, slowly losing mass until they evaporate entirely. But here's the problem: that radiation is random, a thermal hiss carrying no trace of the information swallowed by the black hole. So when the black hole vanishes, where did the information go? Did the universe just break its own rules? Physicists split into warring camps. Some, like Hawking initially, argued the information was destroyed. a heresy that would force quantum mechanics to rewrite. Others, like Leonard Susskind, championed the holographic principle, a radical idea that information isn't lost but smeared across the black hole's surface like a cosmic scratchpad. Picture a two-dimensional barcode storing the essence of everything that falls in a hologram of reality itself. Then came the firewalls. In 2012, a new twist emerged. What if the event horizon isn't a gentle boundary but a seething wall of energy, incinerating anything that touches it? This would preserve information but violate relativity's prediction that falling into a black hole should feel uneventful. The debate rages, with some theorists even suggesting black holes might spawn hidden baby universes, exporting the information elsewhere like a cosmic backup drive. Why does this matter? Because at its core, the paradox isn't just about black holes. It's a glaring clue that our theories of gravity and quantum mechanics, the frameworks explaining everything from atoms to galaxies, are incomplete. Solving it could unlock a theory of everything, a Rosetta Stone for the cosmos. For now, black holes keep their secrets, but each proposed solution, no matter how wild, brings us closer to understanding the universe's most enigmatic recycling program. Here's the cosmic inventory you've never heard about: a glaring discrepancy in the universe's books. According to our best calculations, ordinary matter, the stuff that makes up stars, planets, and even you, should account for roughly 5% of the cosmos. But when astronomers tally up all the visible galaxies, gas clouds, and dust, nearly half of that matter is missing. Poof, gone. This is the missing baryon problem, and it's not just some accounting error. Baryons, particles like protons and neutrons that form atoms, are the building blocks of everything tangible. So where did half the universe's Lego bricks disappear to? One leading theory paints an invisible web across the cosmos. Between galaxies, in the vast voids where darkness reigns, there could be an ocean of diffuse, superheated gas so thin and energetic that our telescopes barely notice it. Picture steam rising from a boiling pot, only instead of water, it's matter so sparse that a single cube of it the size of Earth might hold just a few atoms. This isn't science fiction. The gas would be part of the warm-hot intergalactic medium, or WIM, a sprawling network of filaments theorized to connect galaxies like cosmic scaffolding. The problem: detecting something that faint is like trying to spot a flashlight beam from another continent. Scientists have turned to clever tricks to hunt these ghosts. When distant quasars' ultra-bright galactic cores shine their light through space, the WIM should absorb specific wavelengths, leaving faint fingerprints in the quasar's spectrum. And in 2017, researchers might have caught their first break. Using the Hubble Space Telescope, they detected signs of oxygen ions, twice ionized oxygen, to be precise, in the space between galaxies, exactly where the WIM should lurk. It's not a smoking gun, but it's a whisper, a hint that the missing matter might be hiding in plain sight. Yet even if the WIM exists, it doesn't fully solve the puzzle. The numbers still don't quite add up, leaving room for wilder possibilities. Could some baryons be trapped in exotic forms we've never considered, like primordial black holes smaller than an atom? Or folded into dimensions beyond our perception, the stakes are higher than they seem. If we're wrong about where half the universe's ordinary matter resides, what else might we be missing? This isn't just about filling a gap in a spreadsheet. It's about rewriting the map of reality itself, one invisible atom at a time. Think of the cosmic microwave background as the universe's baby picture, a snapshot of the cosmos when it was just 380,000 years old, a glowing afterimage of the Big Bang frozen in time. This faint radiation blankets the entire sky, and for decades, scientists have treated it like a fingerprint, expecting it to reveal the universe's deepest symmetries. But there's a problem. When they zoom in, the data doesn't play fair. Instead of randomness, there are eerie alignments, strange patterns that cluster around an invisible line some researchers half-jokingly dubbed the axis of evil. The name might sound like a bad sci-fi plot, but the implications are dead serious. These anomalies suggest the universe isn't as uniform as we thought, and that might mean we've misunderstood its very foundation. At the heart of the mystery is a principle called isotropy, the idea that the universe should look the same in all directions, no matter where you're standing. It's a cornerstone of modern cosmology, baked into everything from the Big Bang Theory to our models of dark energy, but the CMB tells a different story. Certain temperature fluctuations, hotter and colder spots in the primordial glow, seem to line up along this so-called axis, almost as if the universe has a preferred direction. It's like rolling a pair of dice a million times and always getting snake eyes. Statistically, it shouldn't happen, yet there it is, staring back at us from the data. So what's really going on? One possibility is that we're seeing the ghost of something primordial, a relic from before the Big Bang. Some theorists suggest the universe might have been born with a spin, a cosmic rotation imprinted on space-time itself. Others wonder if we're brushing up against the edges of a multiverse, where neighboring universes tug at ours like invisible magnets. Then there's the uncomfortable truth that no one wants to say out loud. Maybe we're just wrong. Our telescopes could be picking up subtle distortions from interstellar dust, or perhaps the anomalies are a fluke, a statistical mirage that'll vanish with better data. But here's what keeps cosmologists up at night. If the axis of evil is real, if the universe does have a hidden structure we've missed, it could upend decades of physics. Dark energy, inflation, even the fate of the cosmos might need rethinking. It's a humbling reminder that for all our equations and supercomputers, the universe still holds cards close to its chest. And until we crack this cosmic cipher, that faint glow from the dawn of time will keep whispering secrets we're just beginning to decipher. There's a hole in the universe, a colossal, yawning emptiness so vast it could swallow thousands of galaxies whole, yet it's almost entirely vacant. This is the Boötes Void, a spherical abyss stretching 330 million light-years across, where the night sky isn't just dark, it's missing. To put that in perspective, if you dropped the Milky Way in there, our nearest galactic neighbor would be so far away, its light would take millions of years just to reach us. Astronomers call it a supervoid, but that's an understatement. It's more like a cosmic desert, a place where the rules of the universe seem to have been forgotten. What makes the Boötes Void so unnerving isn't just its size, it's the sheer improbability of its existence. According to our best models of cosmic structure, regions this empty shouldn't happen naturally. The universe, after all, is supposed to be a web of galaxies strung along filaments of dark matter, with clusters and superclusters forming dense knots. Even the emptiest patches should still have something. Yet when astronomers peer into the void, they've found only 60 or so galaxies drifting in that unimaginable expanse. To put that in perspective, a typical region of space that size should contain thousands. It's as if someone took an eraser to the cosmos and scrubbed out most of its contents. So what could have carved out such a void? One theory points to an ancient, unfathomable collision between universes, a bruise left behind by a long-ago encounter with another bubble of spacetime. Others suggest it might be the footprint of a supermassive black hole from the early universe, one so voracious it devoured everything in its path before vanishing. But the most unsettling possibility, that the Boötes Void isn't empty at all. It could be packed with dark energy, the mysterious force accelerating the universe's expansion, warping space so drastically that galaxies never formed there in the first place. Imagine a stretch of ocean so turbulent no fish can swim in it, only instead of water, it's space-time itself, twisted into a dead zone. Yet even these explanations feel inadequate. If dark energy or black holes were responsible, why don't we see more voids like this? And why do the few galaxies inside the Boötes Void seem older than they should be, as if time moved differently there? Some researchers wonder if we're seeing a glitch in the cosmic code, a place where the simulation, if you'll pardon the sci-fi analogy, didn't render properly. Whatever the truth, the void forces us to confront a humbling reality. The universe might not play by the rules we've written for it. And as we stare into that darkness, we're left with a question that echoes across the light years. Is this emptiness a flaw in our understanding, or a clue to something far stranger lurking beyond the edges of the map? If the Boötes Void left you unsettled, wait until you hear about its more mysterious cousin, the Eridanus Supervoid. This cosmic anomaly isn't just empty, it's cold. While most of the universe hums with the faint afterglow of the Big Bang, this region, stretching over 1 billion light years, shows a temperature drop so sharp it's like stumbling into a freezer in the middle of the desert. The chill isn't just a curiosity, it's a direct challenge to everything we thought we knew about how the universe expanded after its birth. The cold spot was first spotted in the cosmic microwave background, that ancient light from the dawn of time, and it refused to fit any conventional models. At first, scientists brushed it off as a glitch, a trick of the data, but then they traced its location and found the Eridanus Supervoid lurking in the same direction. The coincidence was too striking to ignore. If voids are cosmic deserts, this one isn't just barren, it's sucking the heat out of the sky. So what's really going on? One theory ventures into the realm of science fiction. The cold spot might be a bruise from a collision with another universe, a bubble of space-time beyond our own, pressing against ours in some higher dimensional arena. Imagine two soap bubbles gently bumping in midair. Where they touch, energy dissipates, leaving a cooler patch. In this scenario, the Eridanus Supervoid could be the fingerprint of a multiverse we'll never see directly. But before we leap to parallel realities, there's a simpler, if less thrilling, explanation. The void might just be a statistical fluke. The universe is vast, and randomness can sometimes paint patterns that look intentional. Some researchers argue that the cold spot and the void aren't even truly aligned, that our perspective from Earth creates an illusion of connection. Yet even this skepticism can't erase the nagging question. If it's a fluke, why is it this big, this cold, and this hard to explain? The stakes here are cosmic. If the Eridanus Supervoid is a sign of new physics, or worse, a crack in our current theories, it could force us to rewrite the story of cosmic inflation, the explosive expansion that shaped the early universe. Maybe inflation wasn't as uniform as we thought. Maybe dark energy behaves differently in these voids. Or maybe, just maybe, the universe is stranger than we've dared to imagine. For now, the cold spot remains a riddle written in the faintest whisper of radiation, a reminder that even the emptiest corners of space can hold the loudest questions. Just beyond Neptune, where sunlight fades to a dim twilight, the Kuiper belt stretches like a frozen junkyard of cosmic debris, icy rocks, dwarf planets, and leftovers from the solar system's birth. But here's the odd part. This belt doesn't taper off gently into the void. It ends abruptly, like a cliff's edge where the rocks just stop. Astronomers call this the Kuiper Cliff, and it's one of the solar system's most puzzling boundaries. Beyond it, the number of objects drops so sharply it's as if someone built a celestial "keep out" sign. So what's really lurking out there in the dark? One tantalizing answer might be hiding in plain sight: Planet 9. Not the demoted Pluto, but a hypothetical giant, 5 to 10 times Earth's mass, orbiting so far from the Sun it's never been seen. The math is compelling. Something massive could be herding Kuiper belt objects into odd, clustered orbits, even flinging some into the abyss like a gravitational bouncer. If it exists, Planet 9 wouldn't just explain the cliff, it would rewrite our solar system's map. But after years of searching, telescopes have come up empty. Is it a stealthy world camouflaged by distance and darkness, or are we chasing a ghost? Then there's the alternative. The cliff isn't a boundary at all, but a fossil. Billions of years ago, when the solar system was young, Neptune might have migrated outward, its gravity scattering icy debris like a bulldozer. The Kuiper Cliff could mark the edge of that ancient construction zone, a relic of chaos frozen in time. But this theory has its own holes. If Neptune sculpted the belt, why doesn't the drop-off match simulations? Why are some objects past the cliff defying the pattern? The wildest possibility, the Kuiper Cliff isn't just about what's there, but what isn't. Some models suggest the early solar system had a fifth giant planet, ejected long ago by a gravitational tug of war. Its departure could have dragged countless objects with it, leaving behind this eerie emptiness. Or perhaps the cliff is a cosmic mirage, an illusion caused by our limited view. After all, the farther out we look, the harder it is to spot small, dim objects. Maybe the belt continues and we just can't see it yet. Whatever the truth, the Kuiper Cliff is more than a curiosity. It's a detective story written in ice and rock. Every probe we send, every telescope we point toward the outer dark, brings us closer to answering whether we're missing a planet, misreading history, or staring at a clue to something even stranger. Because in the silence beyond Neptune, the solar system still has secrets to spill. Our moon seems like a quiet, barren world today, a place of dust and silent craters where compass needles would spin uselessly. But dig a little deeper, literally, and you'll uncover a puzzle that shakes our understanding of how planets work. Apollo astronauts brought back moon rocks in the 1970s, and when scientists examined them, they got a shock. Tiny mineral grains in those samples were magnetized, frozen in time like microscopic compasses pointing to an ancient lunar North Pole. The implication was staggering. The moon once had a magnetic field, perhaps even stronger than Earth's today. Here's the problem: our moon's core is too small, too cold, and too still to generate that kind of planetary magnetism now. So how did it ever happen? One theory points to cosmic violence. Around 4 billion years ago, the solar system was a shooting gallery, with planets and moons taking brutal hits from asteroids the size of cities. A colossal impact might have stirred the moon's core like a spoon in molten metal, jump-starting a temporary magnetic dynamo. Think of it like shaking a snow globe. The chaos inside could have created swirling currents of liquid iron, generating a magnetic field for a few 100 million years before fading away. There's evidence to support this. The moon's crust shows signs of massive, basin-forming collisions right around the time magnetism was at its peak, but not everyone's convinced. Some models suggest even a giant impact wouldn't have delivered enough energy to power a dynamo that's strong for that long. That's where the plot thickens. Another camp argues the moon's early magnetic field wasn't homegrown at all. It might have borrowed one. In its youth, the moon orbited much closer to Earth, possibly close enough to be bathed in our planet's magnetic influence. Like a child holding a parent's hand, the moon could have been magnetically coupled to Earth, its rocks recording our field rather than its own. But there's a catch. Some lunar rocks show magnetization patterns that suggest the moon's field had its own unique orientation, not perfectly aligned with Earth's. Then there's the wild card crystallization. As the moon's molten interior cooled, heavier minerals like iron sulfide might have sunk while lighter ones rose, creating internal churn. This slow-motion sorting could have acted like a planetary scale battery, generating electrical currents and, in turn, magnetism. It's a subtle process, one that wouldn't require the Moon's core to behave like Earth's. And here's the kicker. If true, it means even small, seemingly dead worlds might hide the ghosts of magnetic pasts. Why does this matter? Because magnetic fields aren't just cosmic decorations, they're shields. Earth's field deflects solar winds and cosmic rays, protecting our atmosphere and making life possible. If the Moon once had one, it might explain why some of its rocks contain traces of water, locked away in minerals that shouldn't exist in the harsh vacuum of space. A magnetic field could have sheltered the young Moon long enough for chemistry to cook up surprises. And if we're ever going to understand exoplanets, those distant worlds orbiting other stars, we'll need to crack how magnetism works in all its forms. The Moon, it turns out, isn't just a relic of our past. It's a key to unlocking mysteries far beyond our own sky. Saturn's North Pole holds a secret straight out of geometry class, a perfect hexagon, etched into the atmosphere like a colossal cosmic tattoo. This isn't some trick of perspective or camera angle. It's a raging storm 30,000 kilometers wide, with winds screaming at 320 kilometers per hour, yet its six-sided shape remains eerily precise. Hurricanes on Earth twist into spirals or ovals, but Saturn's polar vortex defies the rules, locking into a shape so unnatural it looks engineered. And the strangest part, it's been there for decades, possibly centuries, outlasting every earthly civilization. So how does a gas giant, a planet with no solid surface, sculpt a storm into a near mathematical masterpiece? One clue lies in the lab. When scientists spin fluids rapidly in experiments, they can sometimes coax polygons to form squares, triangles, even hexagons. It's all about shear forces, where layers of fluid slide past each other at different speeds, creating stable patterns. On Saturn, the jet stream at the pole might act like an invisible wall, channeling the chaos into order. Picture water swirling around a drain, but with the planet's rotation and atmospheric currents acting like invisible hands, folding the turbulence into a hexagon. But here's where the mystery deepens. Lab experiments can't replicate the scale or longevity of Saturn's hexagon. Earth's most violent storms dissipate in days, yet this one persists, unshaken, as if the planet itself is stamping its identity into the sky. Some theorists wonder if the hexagon is a standing wave, a vibration frozen in time, like the note from a tuning fork resonating through the atmosphere. Others suggest it's driven by deep, unseen forces, perhaps convection currents rising from Saturn's molten core, twisting the upper atmosphere like a cosmic lathe. Then there's the wild card, magnetism. Saturn's magnetic field is nearly perfectly aligned with its rotation axis, a rarity among planets. Could magnetic forces be sculpting the storm, guiding the winds into this bizarre geometry? Or is the hexagon a shadow of something deeper, a fingerprint of quantum fluid dynamics playing out on a planetary scale? The truth is, no single theory fits all the data. Even NASA Cassini probe, which spent 13 years orbiting Saturn, couldn't crack the code. What makes this hexagon so mesmerizing isn't just its defiance of physics, it's the reminder that nature's imagination dwarfs our own. On a world where hydrogen reigns like diamonds and storms rage for centuries, even the simplest shape can become a cosmic cipher. And until we send another mission to Saturn's swirling North Pole, this six-sided enigma will keep spinning, a silent challenge to anyone who thinks they've figured out how the universe works. If Saturn's hexagon left you questioning reality, wait until you see what's lurking at the south pole of Venus, a swirling, double vortex storm that defies logic in one of the most inhospitable places in the solar system. Unlike Saturn's geometric precision, this vortex is chaotic, a pair of frenzied funnels spinning in tandem like ghostly dancers locked in an eternal waltz. And here's the kicker. It exists in an atmosphere so thick and corrosive, it crushes landers within hours and rains sulfuric acid. So how does something this delicate survive in a world that feels like a pressure cooker dipped in battery acid? The answer might lie in Venus's super-rotating atmosphere, a phenomenon so bizarre it makes the planet's upper clouds whip around faster than the planet itself rotates. While Venus takes 243 Earth days to complete a single spin, its atmosphere races around the planet in just 4. This creates hurricane-force winds that stretch and twist, forming standing waves and turbulence capable of birthing and sustaining this strange polar vortex. Picture stirring a cup of coffee with 2 spoons moving in opposite directions. The clashing currents create spirals that briefly stabilize before collapsing. On Venus, those spirals somehow persist, locked in place by forces we're only beginning to understand. But the real mystery isn't just the vortex's existence, it's the why. Earth's polar vortices are driven by temperature gradients and the planet's rotation, but Venus spins agonizingly slow. Its dense, carbon dioxide-rich atmosphere acts more like a liquid than a gas, with heat trapped in a runaway greenhouse effect. Some scientists think the vortex might be a release valve for this pent-up energy, a cosmic pressure vent spinning endlessly to balance the planet's feverish climate. Others speculate it's fueled by hidden topography, mountains or highlands we can't see through the planet's perpetual cloud cover, kicking the atmosphere like rocks in a stream. Then there's the wild card, magnetism, or rather, the lack of it. Venus has no global magnetic field to speak of, leaving its atmosphere exposed to the full brunt of solar winds. Could these charged particles be interacting with the planet's ionosphere, creating electrical currents that somehow stabilize the vortex? Or is the double funnel a fingerprint of deeper, unseen processes, like convection cells rising from Venus's scorching surface? What makes this vortex more than just a planetary oddity is what it reveals about atmospheres everywhere. If we can crack how it forms and persists, we might unlock secrets about weather patterns on exoplanets, worlds where conditions are even more extreme. Venus, often called Earth's evil twin, is a laboratory for the unimaginable, a place where the rules of meteorology get rewritten daily. And as we stare into that swirling abyss, we're reminded, sometimes the most hostile environments hold the keys to the universe's quietest whispers. Mars has a secret one that wafts through its thin atmosphere in tantalizing bursts, here one moment and gone the next. Methane, a gas that on Earth is practically a billboard for life. Cows produce it, wetlands exhale it, microorganisms churn it out by the ton. So when our rovers and orbiters sniffed it on the red planet, the implications sent shockwaves through the scientific community. But here's the twist: Mars methane doesn't behave like ours. It spikes unpredictably, vanishing almost as fast as it appears, as if the planet itself is playing a cosmic game of hide and seek. The first whiffs came in 2004, when the European Space Agency's Mars Express orbiter detected traces of the gas. Then, in 2013, NASA, a Curiosity rover, confirmed it. Methane levels near its landing site spiked tenfold over just 2 months. But by the time follow-up observations were made, the methane had largely disappeared. This wasn't just odd, it defied chemistry. Methane should linger in Mars' atmosphere for centuries before sunlight breaks it down. Unless, of course, something or someone is actively removing it. So where's it coming from? One camp points to geology. Mars isn't entirely dead underground. Volcanic activity, though rare, could be cracking water and carbon dioxide deep in the crust, forging methane through serpentinization, a chemical reaction between rock and water. There's precedent. On Earth, this process fuels methane vents in places like the Lost City hydrothermal field. But here's the catch. No active volcanoes or recent lava flows have been spotted on Mars. Without a smoking gun, the geological explanation feels incomplete. Then there's the elephant in the room, biology. Certain microbes, called methanogens, thrive in airless, subsurface environments, munching on hydrogen and carbon dioxide to produce methane as waste. Mars' ancient lake beds and underground aquifers could, in theory, host similar organisms. It's a haunting thought that beneath the rusty soil, a shadow biosphere might be quietly exhaling, its presence betrayed only by fleeting gas plumes. But proving it isn't easy. Methane alone isn't proof of life, it's just a clue, and the universe loves leaving red herrings. Enter the wild cards. Could meteors delivering organic material spark temporary methane bursts? Maybe. Could electrostatic dust storms generated through chemical reactions? Possibly. The problem is, none of these fully explain the erratic spikes or the gas's rapid disappearance. Some scientists even speculate about an unknown catalyst in Mars soil, a mineral that gobbles methane as fast as it's made. The stakes couldn't be higher. Future missions, like the European ExoMars rover, will carry instruments designed to sniff not just methane, but its isotopic fingerprints, chemical signatures that could reveal whether it's biological or geological in origin. Until then, Mars methane remains one of the solar system's most tantalizing riddles. It's a whisper in the wind, a flicker of possibility that the red planet might not be as lifeless as it seems. And every time a detector picks up another unexplained spike, the same thrilling question echoes through the labs and lecture halls. Are we alone, or is Mars hiding its secrets just beneath the surface? On the morning of June 30th, 1908, in a remote corner of Siberia, the sky split open. Witnesses described a fireball brighter than the sun streaking across the heavens before a blast wave thousands of times more powerful than the atomic bomb dropped on Hiroshima ripped through the taiga. Trees were flattened like matchsticks over 800 square miles, their trunks pointing radially outward from ground zero, as if some invisible giant had stomped on the forest. Windows shattered hundreds of miles away, seismic waves circled the globe twice, and yet, when scientists finally reached the epicenter decades later, they found no crater, no meteorite fragments, just silence where there should have been answers. This is the Tunguska Event, a cosmic detective story with no clear culprit. The leading theory points to a stony asteroid or comet fragment, perhaps 60 meters wide, exploding in midair with a force of 10 to 15 megatons of TNT. At an altitude of 5 to 10 kilometers, the heat and pressure would have vaporized the object before it could hit the ground, explaining the lack of debris. It's a phenomenon we've seen echoes of since, like the Chelyabinsk meteor that exploded over Russia in 2013, though that was a mere firecracker compared to Tunguska's earth-shaking roar. But here's where the mystery deepens. No trace of water or extraterrestrial minerals consistent with a comet has ever been found in the soil. If it was an asteroid, where's the nickel, iron, or rocky shards? The absence is so glaring, it's as if the universe handed us a crime scene without a murder weapon. Then there's the wildcard theories. Could it have been a chunk of antimatter, annihilating itself in a flash of energy upon hitting our atmosphere? The math checks out. A gram of antimatter meeting matter releases apocalyptic energy, but we've never detected natural antimatter in such quantities. Others speculate about a microscopic black hole zipping through Earth like a bullet through tissue paper, leaving no entry or exit wound. It's a chilling thought, though most physicists dismiss it. A black hole that small would have evaporated instantly in a burst of Hawking radiation, and we'd have seen the fireworks. Perhaps the most haunting possibility is that Tunguska wasn't a natural event at all. In the 1970s, a pair of scientists floated the idea of a nuclear-powered alien spacecraft suffering a catastrophic failure, a cosmic Hindenburg disaster. It's a premise straight out of science fiction, but the lack of debris and the sheer intensity of the blast do mirror what we'd expect from a matter-antimatter engine gone critical. Of course, without physical evidence, it's just a provocative what-if. What makes Tunguska so endlessly fascinating isn't just the violence of the event, but the way it humbles us. Over a century later, with all our satellites and sensors, we still can't say for certain what tore the sky apart that morning. It's a reminder that the universe doesn't just operate on scales beyond our comprehension. It sometimes leaves no paper trail. And as we scan the skies for the next potential impact, Tunguska lingers like a ghost, whispering that sometimes the biggest mysteries leave the smallest traces. Look up at the night sky just before dawn or after twilight, and you might catch a ghostly pyramid of light stretching upward from the horizon, a faint, ethereal glow that follows the same path the sun and planets travel across the sky. This is the Zodiacal Light, one of the solar system's most elusive spectacles. For centuries, it was mistaken for the first hint of morning, a celestial false dawn. But modern science reveals it's something far stranger: sunlight bouncing off trillions of dust grains swirling in the inner solar system. Here's the puzzle: where did all that dust come from? The answer might rewrite what we know about our cosmic neighborhood. At first glance, the explanation seems straightforward. Asteroids collide, shedding debris. Comets vaporize as they near the sun, leaving trails of dust in their wake. Over millennia, these particles should spread into a vast, thin cloud along the ecliptic plane, the same flat disk where the planets orbit. But when researchers tallied up the dust from known sources, the math didn't add up. There's too much of it. The zodiacal light is brighter, more persistent than it should be if asteroids and comets were the only contributors. So what's flooding the inner solar system with this mysterious grit? One tantalizing possibility involves Mars. The red planet's moons, Phobos and Deimos, are likely captured asteroids, and they're constantly bombarded by meteoroids. Every impact kicks up dust, some of which could escape Mars' weak gravity and spiral inward toward the sun. But even this can't account for the sheer volume of material needed to produce the zodiacal glow. That's led some scientists to speculate about a more dramatic source: a hidden population of asteroids orbiting closer to the sun than we've ever seen. These volcanoids, named after the hypothetical planet Vulcan, once thought to circle inside Mercury's orbit, could be grinding themselves into dust under the sun's intense heat. The problem: despite decades of searching, not a single volcanoid has been found. Then there's the interstellar angle. Recent studies suggest up to 10% of the zodiacal dust might not be from our solar system at all. Tiny grains ejected by distant supernova or born in the stellar winds of aging stars could be drifting through our cosmic neighborhood, caught in the sun's gravitational pull. If true, every time you see the zodiacal light, you're not just looking at solar system dust. You're witnessing the ashes of stars that died long before our sun was born. But the plot thickens. In 2021, NASA Parker Solar Probe made a bizarre discovery. As it skimmed closer to the sun than any spacecraft before, its sensors detected a strange, dust-free zone starting about 3 million miles from the sun's surface. At that distance, the star's heat should vaporize any ordinary dust, clearing a pocket of empty space. Yet the boundary was sharper than anyone predicted, as if some unseen force, maybe electromagnetic effects or even the solar wind, was sweeping the area clean. This raises a chilling question. If the zodiacal dust isn't just passively drifting, but actively shaped by the sun's invisible forces, what else don't we understand about how our solar system breathes? The zodiacal light isn't just a pretty glow, it's a cosmic crime scene, and the dust is the evidence. Solving where it comes from could reveal hidden asteroids, uncover interstellar hitchhikers, or even expose new physics governing how small particles behave in space. For now, it remains a quiet enigma, a reminder that even in the seemingly empty spaces between planets, the universe is still writing its mysteries in light. Our galaxy has a secret history written in the stars, not just in the bright pinpricks we see tonight, but in the faint, ghostly rivers of light that weave through the Milky Way's halo-like cosmic scars. These are stellar streams, the shredded remains of smaller galaxies torn apart and digested by our own over billions of years. The Milky Way isn't just an island of stars, it's a predator, a cosmic cannibal that grows by consuming its neighbors. But here's the twist: some of these stellar streams don't match any known galactic mergers. Their orbits, their chemistry, even their ages, they're strangers in our own backyard. Could the Milky Way have devoured galaxies so ancient, so faint, that we've yet to find their corpses? Take the Gaia Sausage, for example. This sprawling wreckage of stars, discovered in data from the Gaia Space Telescope, is the debris of a dwarf galaxy that smashed into the Milky Way 8 to 10 billion years ago. Its stars move in radical, plunging orbits, like bees trapped in a jar, telling the story of a violent collision that may have reshaped our galaxy's core. But not all streams are so easily explained. The Helmi stream, another relic of galactic cannibalism, has stars with chemical signatures unlike anything else in the Milky Way, metal poor and primitive, as if they were forged in a galaxy that lived and died before Earth even formed. Then there's the Phantom Stream, a trail of stars so tenuous it's barely detectable. Its existence hints at a victim so small, so dark matter-dominated, that it barely left a trace. These ghost galaxies might be the universe's dark horses, tiny, fragile things that lack the star power to shine brightly, but were rich in the invisible glue that holds galaxies together. If they're out there, hiding in the data, they could rewrite our understanding of how galaxies grow. For every Sagittarius dwarf or Canis major known casualties of the Milky Way's appetite, there might be dozens of these phantoms, their stars now dissolved into our halo like sugar in tea. The implications are staggering. If the Milky Way has absorbed more galaxies than we've accounted for, our models of galactic evolution might be missing a crucial piece. Current theories assume mergers with a handful of sizable dwarfs, but what if the real story is a slow, steady feast of faint, dark matter, rich morsels? It would mean galaxies like ours aren't just built by dramatic collisions, but by countless silent meals, a cosmic buffet of shadows. The hunt for these ghosts isn't just about the past, it's about the future. The next generation of telescopes, like the Vera Rubin Observatory, will scan the skies with unprecedented depth, exposing streams too faint for current instruments. Every new ripple in the stellar sea could be a clue, a whisper from a galaxy that vanished long ago. And as we piece together this galactic family tree, we're forced to confront a humbling truth. The Milky Way isn't just a collection of stars. It's a graveyard, a museum, and a living record of the universe's endless cycle of creation and destruction. So the next time you gaze at the night sky, remember, some of those stars aren't native to this galaxy. They're survivors, refugees from worlds that no longer exist, orbiting in the belly of the beast that consumed them. And somewhere out there, in the darkness between the stars, their lost siblings might still be waiting to be found. The universe is supposed to expand evenly in all directions, a grand, stately inflation where galaxies drift apart like dots on an inflating balloon. but something's wrong. When astronomers mapped the motion of galaxy clusters across the cosmos, they stumbled upon a bizarre pattern. Hundreds of these colossal structures, each containing thousands of galaxies, are all streaming in the same direction at breakneck speeds, over 2 million miles per hour, as if drawn by some unseen cosmic magnet. This isn't random drift, it's a coordinated march toward a point beyond the edge of everything we can see. Scientists call it the dark flow, and it's one of the most unsettling anomalies in modern cosmology. At first, researchers wondered if their instruments were playing tricks. Maybe errors in the data or local gravitational pulls were skewing the results. But the more they looked, the more the anomaly held. The dark flow extends billions of light years, far beyond the reach of any known supercluster or void. Even the Great Attractor, that mysterious gravitational sink we discussed earlier, can't account for it. This motion defies the bedrock principle of cosmology, that on large scales, the universe should look roughly the same in every direction. So what's really tugging at these galaxies? One possibility bends the mind. The dark flow might be evidence of something outside our universe. Picture a cosmic shoreline where the ocean of our observable universe meets something else. Another universe, perhaps with its own gravity, pulling on ours like a neighbor's magnet tugging iron filings through a sheet of paper. It's a radical idea, but not implausible. If the multiverse exists a growing conviction among many theorists, then our universe could be one bubble in an infinite froth of others, each with its own physics. The dark flow might be the first tangible hint that we're not alone in the metacosmos. Then there's the skeptic's take. Could the dark flow be an illusion, a quirk of how we measure cosmic microwave background radiation? The original studies relied on subtle distortions in this ancient light to track galaxy motions. Critics argue that incomplete data or unaccounted for effects, like the Sunyaev-Zeldovich distortion from hot gas, might mimic a flow that isn't really there. But even after refining techniques, the signal persists, leaving us with a paradox. Either our measurements are fundamentally flawed, or the universe is hiding something big. Here's what makes the dark flow so unnerving. If it's real, it means there's structure beyond structure, a gravitational imprint from a realm we can't see, touch, or comprehend. It's as if we've spent centuries mapping a vast ocean, only to discover the tides are being pulled by a moon we never knew existed. The implications would rewrite cosmology, forcing us to confront the possibility that our universe isn't the whole story, just a single page in an infinite library. For now, the dark flow remains a shadow on the data, a whisper at the edge of understanding. But with new telescopes probing deeper into the cosmos than ever before, we might soon learn whether this mysterious motion is a flaw in our maps or a signpost to something far stranger. Either way, it's a humbling reminder: the universe doesn't owe us symmetry, and sometimes the most profound truths lurk just beyond the edge of the visible. Imagine a particle that refuses to follow the rules: no fixed mass, no defined size, behaving less like a solid object and more like a ripple in a pond. This is the bizarre world of unparticles, a theoretical concept so strange it makes quantum mechanics look tame. Proposed in 2007 by physicist Howard Georgi, unparticle theory suggests there could be a hidden sector of reality where particles don't act like particles at all. Instead, they exist in a fuzzy, fractional state, somewhere between a wave and a particle, defying the tidy categories of modern physics. What makes unparticles so tantalizing is how they could solve some of cosmology's biggest headaches. Take dark matter, the invisible glue holding galaxies together. Despite decades of searching, we've never directly detected it. Unparticles could offer a way out. Unlike traditional dark matter candidates, which are often imagined as heavy, slow-moving particles, unparticles might interact so weakly with ordinary matter that they slip through our detectors like ghosts. Their behavior wouldn't just explain dark matter's elusiveness, it could also account for anomalies in high-energy particle collisions, where energy sometimes seems to vanish without a trace. But here's where it gets weirder. Unparticles don't just ignore the rules, they rewrite them. In our everyday world, particles have specific properties: mass, charge, spin. Unparticles, though, scale in ways that defy conventional physics. Picture stirring honey into tea. Ordinary particles are like sugar crystals, discrete and predictable. Unparticles, though, are like the honey itself, stretching and blending in ways that can't be broken down into neat units. This fractional behavior could leave fingerprints in everything from the way galaxies rotate to the faint whispers of the cosmic microwave background. Critics argue unparticles might be little more than mathematical sleight of hand, an elegant idea without a shred of experimental proof. After all, the Large Hadron Collider hasn't spotted them, and astrophysical observations haven't delivered a smoking gun. But supporters counter that absence of evidence isn't evidence of absence. The Higgs boson took 50 years to confirm. Unparticles might just be waiting for the right tool, the right experiment, the right moment to step out of the shadows. What's truly electrifying about this theory isn't just the science, it's the philosophical shift it demands. For centuries, we've assumed reality is built from tiny, discrete bricks. Unparticles challenge that, suggesting the universe might be knitted together by something far more fluid, more chaotic, more alien than we ever imagined. Whether they're real or not, they force us to ask, what if the most fundamental pieces of reality aren't pieces at all, but something we don't even have words for yet? The answer could rewrite physics or vanish like a phantom in the data. Either way, the hunt is on. Einstein called it spooky action at a distance, a phenomenon so bizarre, it made even the father of relativity deeply uneasy. Quantum entanglement, the strange cosmic thread that binds particles across unfathomable distances, remains one of physics' greatest paradoxes. Picture two electrons spinning in perfect sync, born from the same quantum event. Separate them by a millimeter or a galaxy, and here's the unsettling truth. Measure one, and its twin instantly snaps into a mirror state, as if no space exists between them. This isn't theoretical. Lab experiments have confirmed it repeatedly, with particles responding faster than light could travel between them, an apparent violation of relativity's cosmic speed limit. So how does this quantum telepathy work? At its core, entanglement suggests reality isn't local. Particles don't just occupy isolated points in space. They're part of an invisible web where properties like spin or polarization exist as probabilities until measured. The moment you pin down one particle, its entangled partner chooses a complementary state, no matter how far apart they are. It's as if the universe keeps its options open until the last possible second, then updates all linked particles simultaneously, like a cosmic spreadsheet refreshing in real time. The implications are staggering. If harnessed, entanglement could birth unhackable quantum networks, where information leaps between nodes without traveling the space in between. Imagine sending a message from Earth to Mars without latency, or computers solving problems in seconds that would take classical machines millennia. But here's the catch: we still don't know how entangled particles communicate. Some theorists propose hidden variables, undiscovered properties predetermined at the particle's creation. Others champion the many worlds interpretation, where every possible outcome spawns parallel universes, and entanglement is just a shadow of branching realities. Then there's the wildest idea of all, that space and time aren't fundamental, but emergent properties of a deeper, entangled reality. Like a hologram where surface pixels encode 3D depth, our 4D universe might be a projection of quantum links we're only beginning to glimpse. If true, entanglement isn't breaking the rules, it's revealing the real game being played beneath the board. For now, the enigma endures. Every experiment peeling back quantum weirdness only deepens the mystery, leaving us with more questions than answers. But one thing's certain, in the quantum realm, the universe laughs at our classical intuitions. And as we stand on the brink of a potential technological revolution, entanglement whispers a tantalizing promise that the key to tomorrow's breakthroughs might lie in embracing the spookiness Einstein feared. Deep in the heart of every atom, in the fiery cores of stars, and even inside your own body right now, trillions of ghostly particles are streaming through matter like it's not even there. These are neutrinos, the universe's most elusive particles, so insubstantial that billions pass through your fingernail every second without a single collision. For decades, physicists were certain they had no mass at all, moving at light speed like weightless phantoms. Then came the bombshell. Neutrinos change identities mid-flight, morphing between three types: electron, muon, and tau neutrinos as they travel. This bizarre behavior, called neutrino oscillation, proved they couldn't be massless after all. But here's where the mystery twists. Their masses are so vanishingly small, they make electrons look like sumo wrestlers in comparison. Why? The answer could tear open the standard model of particle physics and rewrite our understanding of reality itself. Take the sun, for example. It floods space with electron neutrinos, and early detectors on Earth confirmed their arrival, but with a glaring discrepancy. Only about a third of the expected neutrinos showed up. Where were the rest? The missing neutrinos weren't missing at all. They'd simply changed flavor en route, transforming into muon or tau neutrinos undetectable by those early instruments. This discovery earned the 2015 Nobel Prize in Physics, but it left a deeper puzzle. If neutrinos oscillate, they must have mass, because massless particles don't experience time, and without time, there's no during in which to change. Yet when researchers finally pinned down their mass, the numbers defied logic. The heaviest neutrino is at least 500,000 times lighter than an electron, the next lightest particle. In the grand hierarchy of mass, neutrinos are less than a whisper. So why does this tiny mass matter so much? Because the Standard Model, our most precise theory of particle physics, was built on the assumption that neutrinos are massless. Their minuscule but undeniable weight cracks the model's foundation, hinting at physics beyond anything we've discovered. One radical idea points to the seesaw mechanism. What if neutrinos have ultra-heavy siblings, particles so massive they've never been observed? These hypothetical heavy neutrinos could act like cosmic counterweights, pulling the masses of the neutrinos we can detect down to their featherlight scales. It's a compelling theory, but there's zero experimental proof yet. Then there's the eerie possibility that neutrinos might be Majorana particles, meaning they're their own antimatter counterparts. If true, they could explain one of the universe's greatest imbalances, why matter vastly outnumbers antimatter. In the chaotic first moments after the Big Bang, Majorana neutrinos might have tipped the scales, decaying slightly more into matter than antimatter, and seeding the cosmos with the stuff that eventually became galaxies, planets, and us. The hunt for answers is pushing technology to its limits. Experiments like Katrin in Germany are using tritium decay to measure neutrino mass with unprecedented precision, while deep underground detectors like Super Kamiok and in Japan watch for telltale flashes as neutrinos strike water molecules. Even cosmology plays a role. The way neutrinos barely interact with matter means they shaped the early universe's structure, leaving faint fingerprints in the cosmic microwave background. What makes this mystery so thrilling isn't just the science, it's the scale of what we don't know. Neutrinos outnumber atoms in the universe by 1,000,000,000 to 1, yet we've barely begun to understand them. They could be the key to dark matter, the reason matter exists at all, or even a gateway to dimensions beyond our perception. Every time we think we've pinned them down, they slip through our fingers again, leaving behind only questions, and the tantalizing sense that the universe's quietest particles might be shouting its loudest secrets. The universe is expanding, that much we know, but ask scientists how fast, and suddenly the room gets quiet. This isn't just academic quibbling. Depending on how you measure it, the universe's expansion rate, the Hubble constant, gives two different answers, and the gap between them is growing wider with every new observation. Welcome to the Hubble Tension, a cosmic tug-of-war that could crack open the foundation of modern cosmology. Let's break it down. One camp measures the Hubble constant by studying the cosmic microwave background, the afterglow of the Big Bang. This pristine snapshot of the infant universe, captured by missions like Planck, suggests an expansion rate of about 67 kilometers per second per megaparsec. But then there's the other camp, using pulsating stars called Cepheids and cataclysmic supernova in nearby galaxies. Their answer, 73. That 6-kilometer difference might sound trivial, but in the hyper-precise world of cosmology, it's a screaming discrepancy. Imagine two clocks, one ticking slightly faster than the other. Over billions of years, that tiny gap becomes a chasm. So who's right? The unsettling truth is, both methods are rock solid. The CMB approach relies on the universe's baby pictures, extrapolating forward with our best models of dark matter and dark energy. The local measurements, though, are like checking today's weather, direct, empirical, and harder to dispute. If both are correct, then something's missing in our equations. Maybe dark energy isn't constant but evolves over time, growing stronger or weaker in ways we haven't accounted for. Or perhaps dark matter interacts with itself or ordinary matter in ways that subtly warp cosmic expansion. Then there's the nuclear option. Maybe the Big Bang wasn't the clean, singular event we've assumed. Some theorists speculate about a dark Big Bang, a second, hidden phase transition that injected extra energy into the early universe, skewing the expansion rate. Others wonder if we're seeing hints of extra dimensions or exotic particles that briefly flooded the cosmos before vanishing without a trace. The stakes couldn't be higher. If the tension persists, it might mean we've misunderstood gravity itself, that Einstein's relativity, the bedrock of modern physics, needs a tweak for cosmic scales. Or worse, that the universe isn't as uniform as we thought, and our corner of it is oddly special. For now, the Hubble tension remains a riddle wrapped in the very fabric of space-time, reminding us that even the most fundamental truths might still be waiting to unravel. Black holes dominate our cosmic nightmares, regions of space-time so warped, not even light can escape their grasp. But what if the universe has an equal and opposite reaction? Enter white holes, the hypothetical antithesis of black holes, where matter and energy erupt outward in a cosmic geyser rather than vanishing forever. If black holes are the universe's ultimate drains, white holes would be its fire hoses, spewing out everything they've swallowed in a torrent of light and particles. The math allows it. Einstein's equations, which predict black holes, also permit white holes as valid solutions. Yet no one's ever seen one. So are they real or just a quirk of the numbers? The idea isn't as far-fetched as it sounds. Imagine rewinding a black hole's life like a film in reverse. Instead of collapsing inward, it would explode outward, a white hole in action. Some theorists even speculate that the Big Bang itself could have been the ultimate white hole, a singular eruption of space-time and energy. But here's the twist. White holes violate the second law of thermodynamics, which states entropy, a measure of disorder, always increases. A white hole would essentially unscramble entropy, ejecting ordered matter and energy into the cosmos like a cosmic espresso machine. That's why many physicists dismiss them as mathematical ghosts, impossible in practice. Yet the universe loves breaking rules. In 2021, astronomers detected a bizarre gamma-ray burst, GRB 060614, that defied explanation. Lasting a record-breaking 102 seconds, it lacked the usual afterglow of a supernova, as if the energy had emerged from nowhere. Could this have been a white hole briefly flickering to life? Skeptics point to magnetars neutron stars with apocalyptic magnetic fields as a likelier culprit, but the tantalizing possibility remains. If white holes exist, even ephemerally, they could explain some of the most violent, unexplained eruptions in the cosmos. Then there's the quantum angle. Black holes evaporate over eons, leaking Hawking radiation until they vanish. Some models suggest their deaths might trigger a white hole rebound, a final, fleeting burst of existence before fading into nothing. It's a cosmic echo, a last gasp wrapped in physics we don't yet understand. If true, microscopic white holes could be popping in and out of existence all around us, too tiny and short-lived to detect. The irony is delicious. Black holes, for all their terror, are now almost mundane in astrophysics. White holes, though, they're the universe's rebellious twin, the what-if that refuses to die. Whether they're real or not, they force us to confront the limits of our theories, and the thrilling possibility that the cosmos still has tricks up its sleeve we haven't even dreamed of yet. At the heart of every black hole lies a nightmare for physics, the singularity, a point of infinite density where the laws of spacetime simply break down. General relativity predicts it, but the math goes haywire, treating it as a one-dimensional glitch in the cosmic code where gravity becomes limitless and predictability vanishes. It's the ultimate dead end for science unless it's not. Enter Planck Stars, a radical proposal that swaps the singularity for something far stranger and far more profound. Imagine compressing an entire star's mass into a sphere so tiny, it brushes against the smallest possible scale in the universe, the Planck length, a distance so minuscule that quantum fluctuations make the very concept of smaller meaningless. This is the realm of Planck stars, hypothetical objects where matter doesn't collapse endlessly but rebounds like a spring squeezed to its limit. According to loop quantum gravity, a leading theory attempting to unify quantum mechanics and relativity, spacetime itself might be granular at this scale, woven from indivisible atoms of reality. When matter reaches this density, it wouldn't vanish into a singularity. It would bounce, creating a fleeting, ultra-dense star glowing with the energy of a trapped universe. The implications are staggering. If Planck stars exist, they could solve two cosmic puzzles at once. First, the black hole information paradox, the idea that black holes might permanently erase information, violating quantum mechanics' sacred rule that information can't be destroyed. A Planck star's bounce could theoretically preserve that information, ejecting it back into the cosmos when the star evaporates via Hawking radiation. Second, they might bridge the gap between quantum weirdness and gravity's relentless pull, offering a glimpse of the long-sought theory of quantum gravity. But here's the twist: Planck stars wouldn't last. Their existence would be measured in mere seconds before collapsing back into the black hole's grip. So how could we ever detect them? Some theorists suggest looking for gamma-ray bursts with bizarre energy signatures, cosmic hiccups that don't fit the usual supernova or neutron star collision profiles. Others speculate that microscopic black holes formed in the early universe might have already evaporated, their deaths marked by Planck star flashes we've yet to recognize in the sea of cosmic noise. The beauty of this idea lies in its audacity. It takes the most destructive object in the universe and gives it a hidden heartbeat, a moment of defiance against infinite collapse. Even if Planck stars remain theoretical, they remind us that singularities might not be the end of physics, just the edge of our understanding. And somewhere in the quantum foam at the center of a black hole, the universe might still be playing by rules we're only beginning to imagine. Picture reality as a cosmic magic trick, a grand illusion where the three-dimensional world you experience every day is nothing more than a shimmering projection, like a hologram on a gigantic, invisible screen. This isn't science fiction. It's the essence of the holographic principle, a radical idea that suggests the universe might be a two-dimensional surface encoding all the information needed to generate the rich, textured reality we perceive. At its core, this theory challenges everything we think we know about space, time, and even the nature of existence itself. And the strangest part, it might just explain some of the most baffling quirks of quantum mechanics. The seeds of this idea were planted in the study of black holes, when physicists calculated the entropy, the hidden information, of a black hole. They found it wasn't proportional to the volume of the object, as you'd expect, but to the surface area of its event horizon. It's as if all the data about what fell into the black hole wasn't lost inside, but was instead smeared across its boundary, like a cosmic DVD encoding a 3D movie. This led theorists like Gerard T. Hooft and Leonard Susskind to propose a staggering possibility. What if the entire universe works the same way? What if every star, every planet, even you, are just pixels in a vast, two-dimensional data structure projected into the three-dimensional theater of our perception? Think of it like a video game. The lush, sprawling world you explore on screen isn't stored in your console as a fully rendered 3D landscape. It's generated on the fly from lines of code, a compact set of instructions that trick your brain into seeing depth where none truly exists. The holographic principle suggests reality might operate similarly, with the true source code of the universe written on a distant, flat boundary we can't see. Every interaction, every particle collision, every whispered thought could just be shadows dancing on the walls of a cosmic cave. But how could this possibly explain quantum weirdness, those spooky, counterintuitive behaviors like entanglement or wave-particle duality? Here's where the hologram metaphor gets even wilder. In a holographic universe, the fuzziness of quantum mechanics, the way particles seem to exist in multiple states until observed, might just be artifacts of the projection, glitches in the rendering of a deeper, simpler reality. Entanglement, where particles instantly influence each other across vast distances, could be a side effect of their true, two-dimensional forms being neighbors on the cosmic hard drive, even if their 3D projections appear light years apart. Skeptics, of course, raise valid questions. If the universe is a hologram, where's the projector? How does the encoding work? Experiments like the holometer at Fermilab have tried, and failed, to detect the pixelated grain of spacetime at the smallest scales. Yet the math keeps pulling us back. The AD/CFT correspondence, a concrete realization of holography in string theory, shows that certain higher dimensional universes can be perfectly described by lower dimensional theories without gravity. It's as if the universe is playing a game of mathematical telephone, whispering its secrets across dimensions. The implications are dizzying. If the holographic principle is true, it means the fabric of reality is far more malleable and far stranger than we ever imagined. The solidity of the world around us, the very notion of here and there, could be nothing more than an emergent illusion, a collective hallucination woven from data we're only beginning to decipher. It's a humbling thought that every discovery we make, every law of physics we've painstakingly unraveled, might just be the user manual for a simulation we're all embedded in. And if that's the case, the next question is unavoidable: who or what is holding the projector? Imagine waking up one day with all your memories intact, your childhood, your first love, even the coffee you drank this morning, only to realize none of it actually happened. You didn't grow up, you didn't sip coffee, and you didn't even exist until this exact moment. Your entire life, your entire universe, is just a fluke, a self-aware brain that spontaneously assembled from random quantum fluctuations in the void. This isn't the plot of a sci-fi nightmare. It's the Boltzmann brain paradox, a thought experiment so unsettling it makes the Matrix look like child's play. The idea traces back to Ludwig Boltzmann, the 19th century physicist who helped unravel the mysteries of thermodynamics. He proposed that entropy, the universe's tendency toward disorder, could occasionally reverse in isolated pockets, creating order from chaos by sheer statistical chance. Fast forward to modern cosmology, and this concept takes a surreal twist. If the universe is infinite in time and space, as many models suggest, then even the most improbable events must happen eventually, including the random assembly of a fully formed, conscious brain complete with fabricated memories. Not just once, but countless times. In fact, in an eternal cosmos, Boltzmann brains should vastly outnumber real, biologically evolved minds like ours. So how can you be sure you're not one of them? Here's where the paradox tightens its grip. If Boltzmann brains are more likely than ordinary brains, then statistically, you are probably a Boltzmann brain. Your belief in a consistent, ordered universe, just part of the illusion. The stars above, the ground beneath your feet, all figments of a transient mind destined to dissolve back into chaos as quickly as it formed. Even the scientific method crumbles under this logic because your observations could just be imaginary scaffolding, a fiction conjured by particles colliding at random. Critics pounce on the absurdity. A spontaneously formed brain wouldn't have a body to sense the world, let alone coherent memories or a framework of physics to ponder its existence. But proponents counter that in an infinite universe, every possible configuration of particles must arise, including brains with perfectly consistent but false realities. The only way to escape the paradox is to argue that the universe isn't infinite or eternal enough for Boltzmann brains to dominate. Some cosmologists point to dark energies accelerating expansion, which may prevent eternal inflation and limit the time available for such freak events. Others invoke the anthropic principle. If Boltzmann brains were common, we wouldn't expect to find ourselves in a stable, ordered universe. Yet the Boltzmann brain lingers, less a scientific hypothesis than a mirror held up to our deepest uncertainties about reality. It forces us to confront the fragile foundations of knowledge itself. If existence can flicker into being by accident, what does that mean for the laws of physics, for cause and effect, for meaning? Maybe the answer isn't in the math but in the question. A reminder that some mysteries aren't meant to be solved, only pondered in the quiet moments when the universe feels a little too vast, a little too strange. After all, if you were a Boltzmann brain, you'd never know, and that's the most unsettling part of all. What if everything around you, the stars, the air you breathe, even the thoughts in your head, were nothing more than lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that's evolved from sci-fi trope to legitimate scientific debate, championed by figures like Elon Musk and philosopher Nick Bostrom. At its core, the idea is startlingly simple. If civilizations can reach a technological level where they can create hyper-realistic simulations of conscious beings, and if those simulated beings can eventually create their own simulations, then statistically, the odds overwhelmingly suggest we're already inside one. Think of it like this. Imagine a future where video games have evolved to the point where characters possess full self-awareness, their digital worlds indistinguishable from reality. Now scale that up. A civilization a million years ahead of us could be running billions of such simulations, each housing minds convinced they're real. If that's the case, the sheer number of simulated realities would dwarf the one base universe, making it vanishingly unlikely we're the original. It's a modern twist on Descartes' evil demon or the brain in a vat, but with a disquieting layer of mathematical rigor. The hypothesis gains traction from eerie cosmic coincidences. Why does the universe follow such precise, elegant mathematical laws? Why do subatomic particles behave like pixels when observed closely, collapsing from probability waves into definite states only when measured? Even the speed of light could be seen as a processing limit, a cosmic frame rate preventing the simulation from overloading. And then there's quantum entanglement, where particles instantly influence each other across vast distances, as if the universe is skipping rendering steps to save computational power. But who or what would build such a simulation? Bostrom's trilemma offers three unsettling options. Either civilizations always go extinct before achieving simulation technology. They choose not to run ancestor simulations, perhaps for ethical reasons, or we're almost certainly living in one. The first two feel like wishful thinking. The third forces us to confront the unnerving possibility that our creators might not be gods or aliens, but post-human programmers treating our lives as historical reenactments or academic experiments. Critics push back hard. They argue that simulating every particle in a universe would require energy and resources beyond any conceivable technology. But proponents counter that an advanced civilization might not simulate everything at once, just the parts being observed, like a video game that only renders what the player sees. This selective rendering would explain quantum indeterminacy. The universe fills in details only when we look, conserving processing power. Yet the hypothesis's real power isn't in proving we're simulated. It's in exposing how little we truly understand about consciousness and reality. If the universe is code, what's the hardware? Could we ever detect glitches in the simulation, like mathematical inconsistencies in physical constants? And if we're just data in someone else's program, does free will exist, or are we following a script? Perhaps the most profound irony is this. The same science that fuels the simulation argument, quantum physics, computer theory, cosmology, might one day give us tools to test it. Until then, the hypothesis lingers like a shadow on the edge of science, a reminder that reality might be far stranger than it seems, and whether we're flesh and blood or ones and zeros, the questions it raises about existence, purpose, and the nature of the cosmos are undeniably real. In the vast silence of Earth's orbit, something unusual has been circling our planet for decades, an object shrouded in whispers, myths, and enough conspiracy theories to fill a sci-fi novel. They call it the Black Knight satellite, a mysterious presence first detected in the 1950s by radio operators who claim to have picked up strange signals echoing from the void. Some say it's an alien probe placed here by an ancient civilization to watch over humanity. Others insist it's a relic from a lost human empire, a forgotten piece of technology that predates even Sputnik. But what's really up there? The legend took root in 1954 when newspapers reported that the U.S. Air Force had detected an unknown satellite orbiting Earth years before the Soviet Union launched Sputnik, humanity's first artificial satellite. How could something already be up there? Skeptics argue these early reports were likely misinterpretations of natural phenomena or military secrets, but the myth snowballed. Then came the photos, grainy, black and white images from NASA missions in the 1990s showing a strange, irregularly shaped object floating in the darkness. Conspiracy theorists pounced, claiming this was undeniable proof of extraterrestrial surveillance. The truth, as it often does, lies somewhere in the middle. The most widely accepted explanation is far less dramatic but no less intriguing: space debris. Over decades of spaceflight, discarded rocket parts, defunct satellites, and even lost astronaut tools have accumulated in orbit, some tumbling end over end in ways that make them look eerily deliberate. The Black Knight could easily be a thermal blanket dislodged during a shuttle mission or a fragment from an old launch vehicle, catching sunlight at odd angles. But here's where the mystery lingers. Even if the Black Knight is just debris, why does its orbit and appearance still raise eyebrows among amateur astronomers? Some tracking data suggests it follows an unconventional path, unlike typical satellite trajectories. And then there's the odd radio signal lore, claims that it broadcasts on frequencies that shouldn't exist for human-made objects. Could it be a forgotten Cold War relic, a secret military satellite abandoned and left to drift? Or is there a sliver of possibility that something more enigmatic is circling above us, watching, waiting, its origins lost to time? The Black Knight isn't just a story about aliens or government cover-ups. It's a mirror reflecting our fascination with the unknown, the human urge to find patterns and meaning in the chaos of space. Every time we look up, we're reminded that even in our own celestial backyard, the line between fact and legend can blur into something far more compelling than fiction. And until someone definitively solves the riddle, the Black Knight will keep orbiting, not just in space, but in our imagination. Deep in the cosmic shadows, where the sun's light fades to nothing, there might be something lurking, a dark, silent companion to our solar system, a ghost star with a grim legacy. Astronomers call it Nemesis, a hypothetical red or brown dwarf theorized to orbit the Sun at a staggering distance, far beyond the Oort cloud. Its name isn't an accident. This theoretical object was proposed to explain one of Earth's most chilling patterns: mass extinctions that strike like clockwork every 26 million years. The idea is as haunting as it sounds. Could a hidden celestial assassin be circling our sun, periodically hurling deadly comets our way? The Nemesis Hypothesis was born in the 1980s when paleontologists digging through Earth's fossil record noticed something eerie. 5 of the planet's largest extinction events, including the asteroid impact that wiped out the dinosaurs, seemed to follow a rough cycle. The timing was too precise to dismiss as coincidence. Enter astrophysicists Richard Muller and Piet Hutt, who proposed a dark companion star as the culprit. Nemesis, they argued, could be drifting in a vast elliptical orbit, its gravitational pull disturbing the Oort cloud, a shell of icy debris at the solar system's edge, every time it swings close. The result, a rain of comets catapulted inward, some colliding with Earth in catastrophic bombardments. But here's where the mystery deepens. Despite decades of searching, no one's ever found Nemesis. Infrared surveys like NASA, a WISE mission, have scoured the skies for faint, cool stars, turning up plenty of brown dwarfs, but none in the right place or with the right orbit to fit the bill. Critics argue that if Nemesis existed, we'd have spotted it by now. Even a dim brown dwarf would emit some heat, and its gravitational influence should warp the orbits of distant objects in detectable ways. Yet the outer solar system remains stubbornly silent, offering no clear evidence of a hidden interloper. That hasn't stopped the speculation. Some theorists suggest Nemesis isn't a star at all, but a rogue planet, a massive nomadic world like the hypothetical planet 9 drifting in the darkness. Others wonder if it could be a stealthy black hole, invisible except for its gravity. The most unsettling idea, Nemesis might have already moved on. Stars in our galactic neighborhood shift over millions of years. A passing star could have yanked Nemesis from its orbit long ago, leaving Earth's extinction cycle as the only clue to its existence. The irony is delicious. A theory devised to explain death on a planetary scale might itself be dead, or just hiding too well to find. Yet the allure of Nemesis endures, not just for its apocalyptic drama, but for what it reveals about our place in the cosmos. The universe is vast enough to harbor unseen monsters, quiet enough to keep their secrets, and whether Nemesis is real or myth, its legacy lingers a reminder that sometimes the most terrifying mysteries aren't in the stars, but in the patterns we think we see. Beyond the frozen reaches of Pluto, in the darkest corners of our solar system, something massive might be pulling strings without ever showing its face. This is the hunt for Planet 9, a hypothetical world up to 10 times the size of Earth, lurking so far from the Sun that a single orbit could take 20,000 years. The evidence, a cluster of small, icy bodies in the Kuiper belt behaving as if they're being herded by an invisible giant. Their orbits tilt at bizarre angles, clustering in ways that defy the gravitational pull of Neptune and the other known planets. It's as if the solar system's outer suburbs have a hidden landlord, and astronomers are scrambling to evict it from the shadows. The story begins with Sedna, a dwarf planet discovered in 2003 with an orbit so elongated it shouldn't exist. Then came more oddballs, Biden, Goblin, and a growing list of Kuiper belt objects, all pointing in the same general direction, like cosmic breadcrumbs leading to something unseen. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown crunched the numbers and dropped a bombshell. The odds of this orbital alignment happening by chance were less than 1 in 14,000. Their conclusion, a super-Earth 500 times farther from the Sun than Earth, must be yanking these objects into line, but finding Planet 9 is like searching for a black cat in a coal cellar. At that distance, the Sun would appear as just another bright star in its sky, offering almost no light to reflect. Even our most powerful telescopes, like Subaru in Hawaii, must scan vast patches of sky pixel by pixel, hoping to catch a faint, slow-moving dot against the static of background stars. The challenge is staggering. Imagine trying to spot a single dim light bulb lost in the glow of a distant city while standing on a moving carousel. Skeptics aren't convinced. Some argue that observational bias could be skewing the data. Maybe we've only found Kuiper belt objects that happen to cluster, missing others that don't fit the pattern. Others propose a wild alternative. What if Planet 9 isn't a planet at all, but a primordial black hole no bigger than a grapefruit? Such an object would wield the gravitational heft of a planet while emitting no light, making it nearly impossible to detect except through its influence. It's a fringe idea, but one that underscores how little we know about the solar system's dark frontiers. The implications of finding Planet 9 would ripple far beyond astronomy. Its existence could rewrite the story of how our solar system formed, suggesting a turbulent past where planets were ejected or captured in chaotic dances. It might even explain the tilt of the Sun's axis, a nagging mystery that's puzzled scientists for decades. And if it's out there, what else might be hiding in the void? The hunt isn't just about one world. It's about tearing down the walls of our cosmic neighborhood and realizing how much we've yet to discover. For now, Planet 9 remains a tantalizing maybe, a gravitational whisper in the data, a shadow at the edge of the map. Every new survey deepens the mystery, narrowing the search area but leaving the big question unanswered. Whether it's a frozen super-Earth, a rogue world captured from another star, or something even stranger, the pursuit forces us to confront a humbling truth. After centuries of exploration, the solar system still holds secrets vast enough to rewrite the textbooks. And until we spot that faint smudge of light, or don't, the debate will rage on, fueled by the thrill of the unknown. Picture the universe not as a scattered collection of galaxies, but as a vast, interconnected neural network, a cosmic spiderweb stretching billions of light years, with galaxies clustered like dewdrops along invisible silk threads. This is the cosmic web, the largest known structure in existence, and its origins are one of cosmology's most profound puzzles. How does something so intricate, so meticulously organized, emerge from the chaos of the Big Bang? The answer might lie in the universe's darkest secret, dark matter. When astronomers first mapped the universe in 3 dimensions, they expected galaxies to be randomly sprinkled throughout space. Instead, they found a pattern, a labyrinth of filaments connecting dense galaxy clusters, separated by enormous voids so empty they'd give the Boötes Void a run for its money. These filaments, some spanning hundreds of millions of light years, form a scaffold that's eerily similar to the neural networks in our brains or the root systems of ancient forests. It's as if the universe itself follows a hidden blueprint, one written in gravity's invisible ink. Here's where dark matter steps in. Simulations suggest that in the early universe, dark matter, that mysterious, non-luminous substance making up 27% of everything, clumped together under its own gravity, forming an unseen skeleton. Ordinary matter, the stuff we can see, was then drawn to these dense patches like iron filings to a magnet. Over billions of years, gas pooled along these dark matter filaments, igniting stars and birthing galaxies at the intersections. The cosmic web isn't just a structure, it's a fossil record of the universe's growth, a snapshot of gravity's patient handiwork, but the devil's in the details. Why do some filaments appear denser than others? Why do voids between them vary so drastically in size? Some theorists point to quantum fluctuations in the newborn universe, tiny ripples in spacetime stretched to cosmic proportions during inflation. These ripples would have seeded the distribution of dark matter, setting the stage for the web's formation. Others speculate about exotic physics, like dark matter particles interacting with each other through unknown forces, creating subtle variations in the cosmic architecture. Then there's the wild card, dark energy. As the universe expands, this enigmatic force stretches the cosmic web ever thinner, pulling galaxies apart like taffy. Will the web eventually fray, leaving isolated islands of stars adrift in an ever-growing void? Or does dark energy's push and dark matter's pull maintain a delicate balance we don't yet understand? The cosmic web isn't just a curiosity, it's a mirror reflecting the universe's deepest laws. Every filament, every cluster, every void holds clues about dark matter's nature, the fate of expansion, and even the possibility of other cosmic webs in a multiverse. And as telescopes like the James Webb probe deeper into space and time, we're not just mapping structure, we're unraveling the universe's DNA, one luminous thread at a time. Imagine a library where every book tells a different version of reality, each with its own rules, its own physics, its own alternate history. Somewhere in those endless stacks lies our universe, just one volume among infinite others. This is the dizzying promise of the multiverse theory, the idea that our cosmos might be a single bubble in an ocean of universes, each with its own unique constants, dimensions, and even laws of nature. At its core, this isn't just science fiction, it's a radical response to one of physics' deepest puzzles. Why does our universe seem perfectly calibrated for life? The fine-tuning problem is hard to ignore. Change just one fundamental constant, the strength of gravity, the mass of an electron, and stars wouldn't ignite, atoms would fly apart, and life as we know it would be impossible. The odds of all these variables aligning by chance are astronomically small. So how did we get so lucky? One answer is the multiverse. If countless universes exist, each with random physical parameters, it's no surprise that at least one ours hit the jackpot. It's like rolling a billion-sided die until you finally land on the one combination that works. But where would these other universes come from? Inflation theory offers a tantalizing clue. In the first fractions of a second after the Big Bang, space-time may have expanded exponentially, stretching far beyond the observable universe. In this scenario, pockets of space could have pinched off into separate bubbles, each cooling into its own distinct cosmos with different properties. Some might have stronger nuclear forces, making stars burn out in seconds. Others could have extra-spatial dimensions, with particles behaving in ways we can't even imagine. Our universe isn't special, just one possibility in an unfathomable ensemble. Then there's the quantum multiverse, a twist even more mind-bending. Every time a particle faces a choice, like whether to spin left or right, the universe might split into branches, creating parallel timelines where every possible outcome plays out. In one reality, you turned left on your way home. In another, you went right and had a life-altering encounter. This many worlds interpretation, first proposed by Hugh Everett in the 1950s, suggests that every decision, every quantum fluctuation, spawns new universes ad infinitum. Critics argue this strays into philosophy, not science. If other universes are permanently inaccessible, how could we ever test their existence? Some theorists hunt for cosmic bruises, anomalies in the microwave background where our bubble universe might have collided with another. Others look for subtle gravitational echoes or strange particle behavior that could hint at hidden dimensions. But for now, the multiverse remains a spectacular, what if, a framework that solves some problems while introducing others. Whether it's ultimately proven or discarded, the multiverse challenges our deepest assumptions about reality. It suggests that the universe isn't a single, lonely experiment, but one flickering possibility in an ocean of alternatives. And if that's true, somewhere out there, another version of you might be watching this very video, or living in a world where the laws of physics never allowed life to arise at all. The multiverse doesn't just expand space, it expands the imagination, forcing us to confront the humbling idea that our existence might be both miraculous and utterly ordinary. From unexplained signals to cosmic voids, these 36 interstellar mysteries are more than just scientific curiosities. They're humbling reminders of how vast the unknown truly is. Every time we think we've mapped the edges of understanding, the universe throws another curveball, a star that flickers like a broken streetlight, particles that vanish into thin air, or a gravitational pull with no visible source. These aren't gaps in our knowledge, they're doorways. Each one forces us to rethink the rules, to invent sharper telescopes, more sensitive detectors, and bolder theories. The hunt for answers has given us quantum computers, space-based observatories, and even the internet, proof that the biggest questions often spark the most revolutionary tools. But here's the beautiful paradox. The more we learn, the stranger the cosmos becomes. Solving one mystery often reveals three others, like peeling an infinite onion. Take dark matter. Decades of searching have ruled out countless theories, yet the answer remains just out of reach. Or the wow signal 45 years later, we still don't know if it was a cosmic fluke or a hello from across the stars. And that's the thrill. Science isn't about ticking boxes, it's about chasing the next what if, even when the path leads to dead ends or dizzying possibilities. Some of these enigmas might be solved in our lifetime. Advanced gravitational wave detectors could finally spot Planet 9. Quantum labs might crack the neutrino mass puzzle. But others, they could outlast us, lingering for centuries as monuments to the universe's stubborn secrecy. And that's okay. The unknown isn't a void to be filled. It's an invitation to keep exploring, to stay curious. So look up tonight. Those quiet stars hold more questions than answers, and every pinprick of light is a mystery waiting to be unraveled. Which one captivates you the most? The eerie silence of Fermi's paradox, the hexagonal storm on Saturn, or something we didn't even cover today? Drop your thoughts in the comments. We're all detectives in this cosmic mystery together. And if you're hungry for more deep dives into the universe's strangest secrets, hit subscribe. The next big revelation could be just one video away. Until then, keep wondering. After all, the universe